Hello there, today I'm gonna talk about a ton of things, but they're gonna be all about numbers and math. So there's a lot of things you can see. There's just gonna be some tons of things. So I'm not gonna talk about what exactly I'm gonna talk about. So you can also go ahead and use these. I think they're called timestamps maybe, but you can still use them if you need to something to learn. So let's begin already. So first of all, let's talk about binary. Binary is a very popular type of numbers in Minecraft when making with Redstone. We can shortly call this bin, bin. And we also, this is actually base 2, meaning there are two digits, so there's 1 and there's also 0. So how do we actually determine what binary number is a decimal? It's actually not super difficult, thankfully. First of all, we need to know what bits are. So it begins with 1, and then it starts multiplying by 2 every time. So this time we got a 64 here. I'm gonna make this 7-bit because why not? And we got this binary number here. So 11001000. So how do we determine what this number is in decimal? If a 1 is under each bit, so it's 64 here, we just select it. And if it's 0, we just ignore it. Then what we should do, we go ahead and add every single selected numbers right here. And yeah, we just add it and then we get a 100. So because 64 plus 32, because there's one above, and also plus 4, it all equals 100. Good, awesome. This is literally binary. It's actually super simple, but it does look really complicated. Now let's move on to decimal. We can shortly call this DEC. It's base 10, as you can see, meaning there's 9 digits, so it's actually 10 digits. I meant it's going up to 9. That's literally what I wanted to say. It begins with 9, actually 0, and goes to 9. That's literally decimal. Everybody knows this. So 57,488 is going to be our number. What do I do to convert 57,488 back to 57,488? First of all, I go ahead and put these numbers like this, so this way. After this, I go ahead and multiply the number on the very below by 1. And every time it goes upper, I just add 0 to the multiplier. So then I go ahead and go 100, 1,000, 10,000. After this, what I do is I multiply these numbers with these. So 5 multiplied by 10,000 equals 50,000. 7 multiplied by 1,000 equals 7,000. 4 multiplied by 100 equals 400. 8 multiplied by 10 equals 80. And 8 multiplied by 1 equals 8. After this, we go ahead and add each number simultaneously. And now we get a 57,488. Guys, I do know this makes no sense converting the number that is on the same type of number back. I know it makes no sense, but at least you can have more context over what actual decimal is. It is in fact useful for some people. So yeah, this is kind of cool. So how do you actually implement decimal with Redstone? Well, we can use BCD digits, and it's basically the same as binary. For that, BCD digits. And BCD right here, it stands for binary coded decimal. As the name suggests, that's what we're doing here. So you can see this is in 5, it's basically 4 and 1, so it's in 50 thousandths place, actually 10 thousandths place. After this, we got a 7. 7 is 4 plus 2 plus 1, that's why it's 7. Then we got a 4, well, it's 4, then 2 8s. So there we go, 8, 8, 4, 7, 5. So 57,488. That's literally how we do it. It's super simple. It's actually a lot easier for the binary. Oh, speaking about the binary, I forgot how to do it in Redstone as well. We can do it this way. So when the something is lit, For example, this, it's a 1. If it's not, it's a 0. You can also do it the same way horizontally, even vertically. And you can see they're going the same positions and forms as we type in there. So it's kind of useful. I do use binary almost every time. Sometimes I use hexadecimal as well, but binary hexadecimal, they're most useful, especially binary. So now let's move on to hexadecimal. It's probably the hardest one ever out of these. So hexadecimal is short for HEX. So we can call it hex or HEX. And then we got base 16, which means there are 60 characters or just numbers, ranging from 0 to F. So you already know these, so 0 beginning to 9, ranging to 9, so it's basically the decimal number itself. But then we got alphabet letters, beginning from A to F. A is 10, B is 11, all the way to 15. Although make sure to know there's a limit of F. I mean, if you try to make more English alphabets, right? For example, it's going to be G to 16, H to 17. That's not going to be hexadecimal because hexadecimal it ranges from 0 to F. You have no permission to add G, H, I, J, K, whatever. You don't have the permissions to do this. This is where we can implement our with Redstone. It's like this. You might think there's nothing easy to look at, but it's just signal strength. Yes, literally, this redstone dust is your hexadecimal number. Signal strength. Signal strength. It's super simple. So if I do like C, you can see it's C is 12. So we're getting a 12 right here as well. So you can see these are 12 lamps. And these are a way I can check what hexadecimal number is at both signal strength. I look at it and I hit F3. As you can see, the power is 12 right here. So that's literally what I said. It's basically C. Also, there are texture packs that also show a C or a number right on redstone dust. Although I don't recommend using these texture packs because if you make even bigger redstone builds with these, your computer is going to be struggling to run with these texture packs. My computer is average, and I once tried this texture pack, and it literally crashed my Minecraft and stopped responding. Even though my PC is average, it's not bad, it's not trash. Just don't go to super huge redstone bits that are like millions of blocks away, whatever. These texture packs really, really they really make your PC to struggle to run. Anyways, enough of that babble. Let's also go over how to calculate hexadecimal. So D49C, this number that we're gonna calculate, it does look like it's like very microtic, very little number, right? Well, it's not. It's literally 54,428. This is super huge. So let me show you how they calculate it. So you know D is 13. There you go. So I put 13 like this so that we have better context. C is, you can see it's 12, so I put 12 right here. First, we go over the last number, and 12 multiplied by 1. So just multiply by 1, we get a 12. And then we start multiplying it to what we're going to multiply by 16 times. So 9 multiplied by 16 is 144. Now we're multiplying 16 by 16, so next time we're going to multiply 4 by 256, and we're getting 1024. And then we multiply 256 by 16, now we're going to multiply it by 4096. 13 multiplied by 4096 equals 53,248. Why is this number super gigantic? I cannot believe my eyes. Okay. So yeah, we can see it's 54,428. Super large number. I cannot believe this is looking really microtic, small, whatever, and then in reality it's just super huge. Okay, now I've talked about all of the numbers. Let's start with making you know math. So let's start with addition. So addition is probably the easiest one. It's 4 plus 3 equals 7. It's super easy. So you can see what we need to do. We should step a further number 3 times. So we ignore this 4. Now 4, it doesn't exist. We stepped further 3 times, we get a 7. This is our output here. And then we can see we have stepped 3 times, so yeah, we just write a 3. It's not important to write a 3, obviously. I just put how many times we stepped, that's why. So, and that's how it looks like on paper. So let me explain it. So we got 9 plus 0 equal 9, obviously. 6 plus 2 equals 8, and 4 plus nothing equals 4. That's literally how to do it. Although, when we have something like this, let me show you how to also do. 9 plus 7 equals 16, right? Although, when there are more digits to go, we have no permission to type 16 because that will mess everything up. Instead, we should save our 1 into the memory, and then when we do 1 plus 6, we get a 7, right? But we have 1 in the memory, so we add 7 by 1, so we're gonna write a 7. Actually, 8. And we also got 1 plus 6 when we type 7 because there's nothing in the memory. And then we got 7 plus 2 equals 9. And we got an answer of 9,786. Good. I actually don't properly know how to do all of this math with binary on paper because I've never seen how people actually do. So let's just go ahead and skip this one and go to subtraction. Subtraction is actually a very cool one. So you can see if I got a 4 minus 3, how does it equal to 1? Well, we do the exact same thing, except this time we step back. Again, we don't mind about this 4 here. As you can see, we stepped back 3 times, so we write 3. Again, this is not important to type a 3, I'm just showing you that. So let me show you how to actually do a math with paper. So, subtraction. So first of all, so you can see we got a 1. So 143 minus 71. How do I actually do this one? 3 minus 1, it equals 2. So we write it 2. After this, we do 4 minus 7, but there's a problem. 4 minus 7 equals a negative number, and we have no permission to type negative numbers. So instead, we go ahead and delete this one, and now we're transferring this 1 to 4. Essentially, we're adding a 10 to this. And then our 1 becomes a 0 because we decremented by 1. And 1 minus 1 equals 0. If we got like 4 here, it will become a 3. So now this looks like it's 4, but it functions like 14. After this, we do 14 minus 7, and that equals 7 again. So our answer is 72. Good. Next thing we got is multiplication, and this is probably the easiest one to understand. Probably addition is easier, but let's just go ahead and look over what is this. So instead of showing you, it's actually going to be a little more complicated to explain. So let's do it manually. First of all, I go ahead and multiply 5 by 2. So I write a 10, but you might be asking, bro, this is literally this is 10, not 0. And also, did I say I'm going to write a 10? I meant 0 if I did. So we write a 0, but since we have 10 right there but not 0, we save 1 into the memory. After this, we go ahead and multiply 5 by 3, and we can try to type 5, but since there are no more numbers to multiply right here, we go ahead and just directly type that number. So it's 15. And we got our answer of 150, although this is incorrect because we have 1 in the memory. What we should do with it? Well, we have to add 15 by 1, so now it's 16. So we have an answer of 160. After this, we need to move on to 4 and start multiplying everything by 4 instead of 5. Except this time we do it in the shifted way. So whatever we have in here, we just shift it by 1. So 3 by 2 equals actually 4 by 2. It equals 8. So I'm gonna write this in here. After this, we do 4 minus 3. actually multiply by 3. Why I was saying minus, I don't know. So we're just gonna go ahead and type a 2 and a 1. Because, well, that's 12, and we have no more numbers in there, so we have permission to type 12 directly. And you have nothing to memory. So you can see we have typed it to shift it way. And now the last thing we should do with it, well, we just add it. So this does function like it's 1280, but we should write the shifted way. So we can imagine this as 1280. So first of all, we type in a 0 because nothing is, well, you know. I'm just gonna go ahead and put a plus. After this, 6 plus 8, it equals 14. We have no permission to type 14 because there are more numbers to calculate. So I'm just gonna go ahead and type 4 and save 1 into the memory. Next we got 1 plus 2, and that equals 3. Yeah, but remember, we have 1 in the memory, so we're gonna go ahead and we're just gonna go ahead and type one more 4. And now there's only 1, there's nothing else left. So we're just gonna go ahead and put it directly right here. There we go, beautiful, we got 1440. Nice. And now division is the last thing I'm gonna talk about. 640 by 32, we're gonna divide it. So what I should do first, so first of all, so 32, right? So those 32 fit in, this like 66 actually, 6. Is smaller than 32. So let's go ahead and take a bigger number. So 64. We just shifted it. So yeah, there we go. 64 and 32. Let's go ahead and see how many times it fits in. So we're just gonna go ahead and then you can see 32 fits 2 times in 64. So we're gonna go and type 2. After this, we'll multiply 2 by 32, and we're gonna go ahead and get 64. After this, we go ahead and subtract these. And we're gonna go ahead and get nothing, because that's 1, 0. Okay, so now we should repeat this procedure again, although we have a 0 here, right? So what you actually need to do with the 0 when there's nothing left, you just go ahead and put it directly right here. There we go, 20. So 640 divided by 32 equals 20. Nice. Alright, so now let's go over making it each Redstone component with Redstone, except division. I don't have one. First of all, we got addition, and it's actually really simple. Let's go ahead and start with binary addition first. So this is the adder here. I'm not gonna make a tutorial on this video yet, but maybe I'll make it later. Who knows? But I definitely will. So if I do like a 3 plus 5, we get an 8. Awesome. And if I do it backwards, it obviously still works. If I do 7 plus 10, I get a 17. So this is our carryout. It functions like 16. And we get a 1 here. And if I do 7 plus 13, we get a 20. Good. This is literally what I want to see on my screen. And the next thing we also got here is hexadecimal adder. So here's how we do it. So this is your input A, I think, and this is your input B. Whenever you go ahead and invert something, right? So you can invert with this contraption. This is your value, and then you invert it one more time. So let's go ahead and add, I don't know, 5 and 3. And that equals 8. As you can see, it works. Awesome. Let's go ahead and move on to the next thing, which is subtraction. Subtraction is, we have 3 types of subtractors. First subtractor can handle negative numbers. So let's go ahead and first type 5 minus 3. And then we get a 2. Also, this does get used very usually. So I'm going to explain how it works. First of all, we got an adder. You can use any carry cancel adder. Well, our B input right here is inverted, and we also have a carry that's always on. There's no way you can turn it off. After this, you go ahead and put the output of this into the other adder that does the same thing, except the output of this adder is inverted, and then it's also having a carry enabled. So yeah, that's another subtractor. Basically, and it only has one input, which is coming from the output of this, and it's inverted. You put it in here, you have a permanent carry in right here. And then what we do, we're gonna go ahead and output both of these into one same line, except when this carry out, right? If it's on, we wanna go ahead and let this free. Actually, when it's off, well, you can see it's off right here. We're just going to plug this redstone dust directly here. If it's off, well, what are you gonna do? We're gonna let this through, and we're gonna lock it. Else we do the backwards procedure. And then we plug it into here, this line right here, and as you can see, we get a 12 that's positive. Let's go ahead and invert it. So this time I'm gonna go ahead and do 3 minus 5, and we got a negative 2. So this is really good thing. It can support negative numbers, but you might think, bro, this is doing two subtractors. Obviously, with one they'll support these. Well, you're completely wrong, because I mean, this is the exact same thing as one of these adders. So it has input B inverted, and it has permanent carry in. If I go ahead and do 5 minus 2, actually 3, we're gonna get a 2. But if I go ahead and do it backwards, well, I mean, it's not broken because that's called, I think, side numbers. But I mean, the easier way to do it, to check what is it saying right here is from this device. There's also a conditional subtractor. It is kind of similar to this one, except when the number is negative, we just go ahead and revert our A input to the output. So let me talk about it. So if I do 5 minus 3, 5 minus 3 equals 2, so we're going to put it right here. Although when I do 3 minus 5, well, the output is negative, right? So if it is, just give me my A input back. That's literally how a conditional subtractor works. And now let's go ahead and do subtraction from hexadecimal. I mean, I felt absolutely no subtractors in hexadecimal. So I had to make one, and it was really brain breaking. This is the stupidest thing I've ever made. But at least it is working, so let's go ahead and try. I don't know where you input properly, so let's go ahead and do 3 minus 5, I think. Is this gonna work? Oh yeah, you input it backwards. So we're gonna go ahead and get a 2. So yeah, it's kind of cool. It cannot handle, I think it cannot handle these negative numbers. So let's go to check it one more time. So if I do 5 minus 3, it should not be able to handle negative numbers. Yes, it just shuts off. Up next, we got a multiplier. And I mean a conditional one. Actually, conditional, no, combination. There we go. It is looking really complicated, so let me explain it. First, we got 8-bit adders, two 8-bit adders, and as you can see, the one input that we're sending, it goes all of them to all of them, right? It goes through all of them. Except each time, these get shifted up one time. And there you have a comparator on subtraction mode. This comparator is getting locked by here, so if you go ahead and type 5, right? We're essentially unlocking this comparator and this comparator. This one is 1 and this one is 4. So your goal is, when inputting something, like, let me show you better, you go ahead and put it over these comparators so that they have a signal. But when you type something right here, we're going to unlock these comparators from different sides. So for example, I'm doing 4 by 8, which is 8 by 4, and I'm going to get this. Really cool. Wait, 8 by 4? Oh yeah, it's first. I thought it was something broken. I thought I was doing something else. And now finally, this is gonna get very long video. Incrementing or decrementing, INC or DEC. When incrementing, you add 1 but not anything else, or not more. And when decrementing, you subtract by 1. So when we're doing 67 incrementing by 4, we're just stepping further 4 times. As you can see, we have a 4 here. This is the exact same thing as adding 67 plus 4. And now we'll do the same thing, except the procedure goes back when decrementing. As you can see, it's the same thing as subtracting. So with regards to actual incrementing, I only found the incrementer like this. I haven't found a decrementer, but this is the binary incrementer. So as you can see, if I press this button, it keeps incrementing. Oops, I was too fast. As you can see, it keeps incrementing every time. And I think it's free ticks, but it's kind of cool. I love this. Oh, I don't think there's even a clear function. It's not my incrementer at all. So here's how it looks like. Let me also look at it a little bit. So this is the upper view right here. This is the torch here. It's to take flop, flip flop actually. And yeah, that's literally how it looks like. And finally, there's also a hex incrementer and decrementer as one same device. So we got this dropper facing into this dropper, which is facing back into this dropper. This dropper got all of the items stacked, all of the stacks of items actually. Oh, I think I broke it. And this one got nothing items right here. This item repeater is gonna be on 2 ticks. So if I press on, oh, I just decided to decrement. I think I kind of broke it. No, you can see it keeps incrementing in hexadecimal. If I decrement, it keeps decrementing. World download again is in the description so that you can have more context over these things. And yeah, thank you for watching. That's math explained.